Hello students, welcome to this lecture. In last few lectures we have been looking at one approximate method in quantum chemistry, that is the variational method. So far we have discussed variational principle, how this principle is justified, what are the ways to implement this variational principle and to do some variational calculations. We took a few examples. For example, we took a harmonic oscillator problem, and then we took two guess wave functions or trial wave functions, and we realized that when the trial wave function has functional form very similar to the real result, to the real solution of harmonic oscillator, we could reproduce the true solution of harmonic oscillator problem. But when the functional form of the trial wave function broadly obeys the boundary conditions but is quite different from the real solution, in that case we saw that we can approach the ground state energy very nicely with some error. We discussed how these errors we are reducing as we approach the best or the optimum value of the variational parameter. We also looked at one example for hydrogen atom by taking a trial function as a Gaussian function instead of an exponentially decaying function. From these examples, we not only learned how to do variational calculation, but we also understood a few things. I would like to summarize them first before we proceed to our next topic. Some key features that we learned from our exercise is that in some cases, the convergence of energy and convergence of wave functions, they do not go hand in hand. Because the variational principle is designed for to get the best estimate of energy. So therefore, we quickly go to the best solution of for the energy, but when it comes to the other properties of the system, the variational principle is not that great. In particular, we saw that the wave function takes time to converge to the true wave function of the system, and therefore, since the properties, many other properties of the system can be derived from the wave function, so therefore, other properties other than the energy may or may not be always very accurate from a variational calculation. The other thing that we noticed is that it really matters a lot what trial function we are taking. If our trial function is a good one, very quickly we will get very accurate results. But if our trial function happens to be not a good choice, in that case, we simply get stuck to a value, to an energy value, which could be very far from the true energy value. So therefore, the choice of the trial function is crucial in variational calculation. Now, when it comes to choosing a trial wave function, it matters our experience, the intuition to that chemical problem. These things play an important role. But we would try to keep or explore a method or try to see a method which should not be that reliant on, let's say, experience or intuition. Of course, they are very important. We cannot completely disregard the requirement of the systems, but we also need a little bit of flexibility in our approach. Other problem that we saw is that even if we could extend variational principle for excited states, but we realized that it's not always possible to have a trial function for an excited state which satisfies all the conditions that is required for excited state variational calculation. So therefore, most cases we use variational principle to obtain the ground state energy. So it's not that well suited for excited states. The other thing that you would have noticed during the variational calculations is that we have we define one particular wave function. We have a parameter in that wave function. Often this parameter, let's say the examples that we have seen, goes in the exponent of an exponential function. Of course, we can actually introduce more than one parameters in our trial function and then try to optimize the energy with respect to each of these parameter and the function. But as long as we have a single function as trial function, we have some limitation, because oftentimes what happens in more complicated systems, you would see that we require some flexibility to express certain features of the system. This flexibility doesn't come when we have a single function as a trial function. To overcome this limitation and to some extent overcome the other limitations that we just discussed, we use a different variant of variational calculation that goes by the name linear variational method. So, we will discuss in today's class this concept of linear variational principle. What it tells? It simply tells that instead of your trial function being defined as a single function, now let the trial function be a linear combination of two or more functions. For the time being, we will restrict ourselves to defining a trial function that is linear combination of two functions, here psi1 and psi2. So, our trial function is now phi, which is now defined in terms of two other functions, psi1 and psi2. The linear combination, the coefficients are given as c1 and c2. Now, if this is my trial function, variational principle tells that you evaluate the energy with respect to this trial function, and this energy provides the upper bound to the ground state energy. Now, since I have defined my trial function as shown here phi, where the psi1 and psi2 I can choose as perhaps some eigenfunctions that are coming from a complete set of eigenfunction of a Hermitian operator. So, I would assume that I have some idea about this psi1 and psi2. Depending on the system that we would discuss, we will see how we can take this psi1 and psi2, but at the time being we keep it general that let there be some known wave functions psi1 and psi2, and in other cases when we have more number of functions, let us say that we have a complete set of eigenfunctions psi i's. Now, using them we are defining a trial function as a linear combination of this function. So, immediately we can evaluate this energy expression, which requires two integral evaluation. First is to make sure that the trial wave function is normalized, that means the overlap of the trial function with itself. The second is this energy integral or the expectation value of the Hamiltonian operator when the state is defined by this trial function phi. Let us start first with the overlap function. So, when I try to calculate the overlap function as shown here, you see I have in the bra side I have written down the expression for the trial wave function. In the ket again the same function appears. When I look at it, I see there is psi1, psi2 in the bra, psi1 and psi2 in the ket. So, I open these terms integrals, and the first term I am getting by when I am looking at the overlap of psi1 with when it is in the bra and psi1 when it is in the ket with the coefficient of c1 square. So, I have the first term as c1 square, which is actually now the square of the amplitude, the c1, the coefficient of this psi1, plus similarly I have c2 square psi2 overlap with itself, and then twice we would get c1 c2 psi1 psi2, or the other opposite. So, c2 star c1 psi2 psi1. Now, since I am considering that the coefficients, if I consider them as real numbers, then I can write them as 2 c1 c2 with this overlap. Now, what do I see here? I see that I have to evaluate the overlap of the function psi1, the known function that I am starting with itself, similarly psi2, and then overlap between psi1 and psi2. Mind you, this psi1 and psi2 I already know, so therefore these integrals I should be able to evaluate them. Now, what I would tell, we will give some names to these integrals. So, this is overlap of psi1 with psi1. So, these overlap integrals will define as S, and we call 1 1. So, S11 indicates the overlap integral of psi1 with itself, and this integral we call them as S22, and this one is S12. They simply indicate that this is the overlap of psi1 and psi2. Now, this is what we got for the denominator. Now, let us look at the numerator of this energy expression, that is the energy integral. Similarly, I have now on the bra the wave function, the ket the same wave function, trial function, and now in my operator I have the Hamiltonian. The system, the complex system that I am dealing with, I of course know it's Hamiltonian. So, what I am doing is that again following the same way that I obtained the overlap integrals, I now do the same thing. For example, I will just explain one. So, I have here C1 psi 1, the Hamiltonian, and C1 psi 1. When I took these three terms, I would get C1 square outside the integration, psi 1 h psi 1. So, this is now my energy integral. With respect to psi 1, the wave function, this is one of those known wave functions that I am starting with. This is the Hamiltonian, and similarly I will get a term with respect to psi 2, the matrix element of the Hamiltonian operator with respect to psi 2, and then the cross term. Now, the way we define these overlap integrals as S11 or S22, we will do the same thing for these energy expressions. So, we call these terms as H11, that means this is the Hamiltonian matrix element with respect to the basis functions of psi 1, and H22, when I evaluate this integral I call this H22, and this one is H12, and similarly if I have psi 2 in the bra, psi 1 in the ket, I would have H21, but since Hamiltonian is a Hermitian operator, so I am taking them H12 and H21 as same. Okay. Now, what we do, we took these, we will take these expressions and go ahead and evaluate the energies. So, now if you from the previous step, if you see that we had the energy which has which depended on the expectation value of the Hamiltonian operator divided by the overlap of phi with itself, the trial function with itself, then we come to this equation over here, which is now written in terms of what are the terms that we are seeing here, C1 square, C2 square, these are the coefficients. I do not know them yet because I want to find out the wave the true value of the trial wave function. All I know is psi 1, psi 2s and also the Hamiltonian operator. So, therefore, I know H11, I know H22, I know H12, and the overlap integrals also I know because I know the wave function. So, the things that the quantities that I do not know in this equation are C1 and C2, and this energy, the variational energy, depends on these parameters C1 and C2. The task becomes at our hand becomes that we have to find the values of C1 and C2 such that the energy is minimum. It is minimum with respect to both with respect to C1 as well as C2, because energy variational principle tells that the best energy, that given the choice of trial function you have made, the best energy is obtained when you minimize the energy function. Now, what would I do? Since energy depends on C1 and C2, I write down these two equations that let the derivative of E with respect to C1 be 0, and similarly let the derivative of E with respect to C2 is 0. Now, when I impose these two conditions by working with this equation, it is straightforward that I can come to the answers that are given here in this slide. You see that I obtain now two linear equations with two independent variables C1 and C2. They appear in both the equations. So, I have got two equations and two unknowns C1 and C2. So, in this case I have got two linearly dependent equations. Now, I can solve them. You know that when we have these linear systems of linear equations, we can write the corresponding determinant and then solve the problem. So, this is a standard mathematical procedure that we are going to follow. You can see the two these systems of equations, or also we call them as secular equations. So, these equations I can express in terms of these two determinants. The first determinant contains the Hamiltonian matrix elements H11, H12, 21, 22, and the overlap matrix elements S11, S12, S22, and then I have the C1 and C2, the coefficients. Now, the product of these two determinants is going to be 0. Now, when I have such a situation, immediately I know that there is a trivial solution. The trivial solution is that this equation holds good if both C1 and C2 are 0. But when both C1 and C2 are 0, my trial wave function is C1 psi 1 plus C2 psi 2, since the coefficients are 0. So, therefore, the trial wave function is 0. So, I do not have anything to work with. So, that is the trivial solution. We ignored the trivial solution. Now, we would look at the non-trivial solution. When I want to do the non-trivial solution, what would I do? So, then I would focus on this determinant and solve this determinant, essentially evaluate the value of this determinant. And you see that this is a 2 by 2, this determinant has got 4 terms. So, when I expand this, I would get an equation with which is quadratic in E, because H1 all the Hamiltonian matrix elements as well as overlap matrix elements I already know. There are some real numbers. Exactly how I would get them is a different question. We will look at them when we discuss some example problems, but in principle I know them. What I do not know is these energies. So, when I open this determinant up, I will be able to write down a quadratic equation in terms of E, and then I would get the solution of E. That means at what values of E that quadratic equation will be equal to 0. So, since the equation is quadratic in E, I would get 2 values of E at which this function will become 0. Now, these 2 E's are my solutions. The lowest of the two in terms of the magnitude is the energy of the ground state. The other one, the highest of the two, is the excited state. It is possible to show that using this linear variational principle, say if I have a 2 by 2 determinant, so I will get 2 energy solution. The lowest energy solution is the upper bound of the ground state. The upper energy solution, or the highest energy solution, is the upper bound of the first excited state of the system. And if I have a larger number of linear equations, so in that way I can also talk about the other excited states. But since in this example we have got a 2 by 2 problem, so therefore we are getting 2 solutions for energy. So we obtained 2 energy values. So they are the variational energy corresponding to the system. Now, the moment I get 2 energy values, E's, I would plug these values of E for each energy solution. I would be able to obtain the C1 and C2, because in that case, what would those C1 and C2 will be used to describe my wave function. The trial wave function, remember, it depends on C1 and C2, because psi1 and psi2 are known functions. It's only C1 and C2 that I do not know. So this problem can also be expressed in terms of a matrix. In that sense, in that case, what would I do? Essentially, I would have this 2 by 2 matrix. I would diagonalize the 2 by 2 matrix, and the eigenvalues would be the energies. The eigenvectors would be the coefficients which will be used for the eigenfunctions. Okay, we keep this in mind, and we'll come back to this procedure when we look at some solution. In many cases, what happens is that if my psi1 and psi2 happen to be eigenfunction of a Hermitian operator, so they would form a complete set of eigenfunctions. In many cases, we would see that our trial wave function psi1, psi2, psi3, so on and so forth, we will take them as some eigenfunctions of a Hermitian operator. So in that case, what happens? These psi i's, they form a complete set of orthogonal basis functions. Now, when they are orthonormal, that means psi S11, that is, since the psi1, psi2, all of them are normalized, so S11, S22, they will become 1. And since they are orthogonal to each other, the overlap of psi1 with psi2, that is S12, will become 0. But that's not necessarily true in all the cases. in some cases you would see that the wave functions are coming from two different Hermitian operators. So, therefore, this orthonormality condition is not applicable. So, in those cases where the wave function the trial wave function is expressed in terms of a complete set of orthonormal eigenfunctions, in those cases S11, S22 can be made 1 and S12, S21 can be made 0. In that case, the determinant becomes even simpler. Okay, we keep this in mind. Now, what we do is that suppose we would extend this discussion not to two functions, but rather when the trial function is a linear combination of n number of functions. So, here I am telling that I know psi 1, psi 2, psi 3 up to psi n, and I am taking that set and I am expressing my trial function phi as C1 psi 1, C2 psi 2, C3 psi 3. So, what would I need to know? I do not know what are C1, C2, C3 because that is what the variational calculation would give me. But to the moment I see that my trial wave function is expressed as a linear combination of many functions, I immediately write down the corresponding secular equations. So, if I have my trial wave function is a linear combination of n functions, so I have a n by n determinant to work with. So, the non-trivial solution of this would be obtained if I express it in terms of as a matrix. So, I will have a n by n matrix that has to be diagonalized, which will give me n number of eigenvalues, and each eigenvalue will give me a one dimensional a vector that would be the eigenvector. So, I will have n number of eigenvalues, and for each eigenvalue I will have a one dimensional array as the corresponding eigenvector. So, therefore, the eigenvector matrix will be n by n, the eigenvalue matrix will be one dimensional array of n number of energy values. So, this becomes the general formulation of the linear variational principle. Why do we call them linear variational principle? Because we are expressing our trial wave function as a linear combination of many known functions. Okay. What we would do now is take this linear variational principle and apply it to a system. In this case, the problem that we want to discuss is that to find out the polarizability of hydrogen atom. We know that general model of an atom, we know that atom composed of a centrally located nucleus surrounding which the electrons go around. So, consider hydrogen atom. So, therefore, I have a central nucleus and one electron that is going around. In fact, this description can also be used for, it can be applied for even other systems, but for simplicity we will consider hydrogen atom. Now, when I apply electric field to this hydrogen atom, what would happen? Now, the atom has a positively charged core, a negatively charged peripheral region. When I apply electric field, the positively charged particle and the negatively charged particle, they would respond differently to this electric field, to the applied electric field. Now, what happens is that when I apply external electric field, the nucleus, the positively charged nucleus, gets pulled along the direction of the electric field, whereas the electron, the negatively charged particle, gets pulled up to the direction opposite to the applied electric field. So, when that happens, a situation like this appears, where the beautiful symmetry of the atom, the charge distribution symmetry is lost. Now, electron and nucleus, they are so to say, they are polarized. So, I have polarized the atom, so that I see a distorted distribution of electron density with respect to the nuclear charge. That is happening because I have applied an electric field. Now, when the applied electric field is weak, only in those conditions, we can say that the system develops, it does not matter what is the value of the electric field. So, when such a polarization occurs, the system of course develops a dipole moment. The dipole moment of the system has this dependence on the electric field for very weak values of electric field, where epsilon is my electric field that I am applying, mu is the dipole moment. This alpha is what is known as the polarizability of the atom. So, this tells me how easily can I polarize this particular molecule, that means or particular atom. That means by applying very little energy, very little electric field, can I induce a dipole moment in this atom. If I can induce a strong dipole moment by applying a very weak electric field, that means this system has got good polarizability. Now, this equation is, as I said, of course, works only when I have a weaker electric field. But now, what would be the energy required to induce this dipole moment, to create this dipole moment mu in this system? That energy expression is given by this relation, where this is delta E, that is the energy requirement to create by applying electric field to create a dipole moment of mu. We obtain we use this relation to do this. Here epsilon prime is simply another form of electric field. So, that means I am applying electric field from 0 to epsilon, and then I am trying to find out that what would be the energy required to obtain this dipole moment mu. So, in place of mu, I use this relation that I just wrote down, and then I see that alpha, the polarizability, which is taken to be a constant for a particular atom, comes out of the integration, and then I obtain this relation minus alpha epsilon square divided by 2, where epsilon is my applied electric field. Now, what have we done is that we have expressed this electric field that we are applying, the polarizability of the atom in terms of energy. Why is it a good thing? That is because we know how to evaluate the energy of a system more accurately using variational principle. So, since if the properties of the system that I am interested in can be connected to the energy, then it is a good thing to have. Now, what happens is that we the question that we have to answer is that to obtain the polarizability of this hydrogen atom, we have to see that how much is the energy of this hydrogen atom is changing when I am subjecting it to this electric field. So, since energy change is now can be expressed in terms of the polarizability and the electric field. So, therefore, I can determine the polarizability if I know how much energy is changing when I subject this hydrogen atom to an external electric field. So, that means what? My system, the Hamiltonian of the system is going to change. Now, the total Hamiltonian of the system is the Hamiltonian of the hydrogen atom before application of electric field plus the extra term, extra potential energy that is arising because of application of the electric field. Now, when I apply electric field and the electrons respond to it, the potential energy that the electron experiences because of this electric field is simply charge of the electron minus E multiplied by the electric field. Now, I am considering that I am applying this electric field along z direction. So, therefore, I will take the z component of this electric field, which is epsilon z, and this I can write down as epsilon into r cos theta in spherical polar coordinate, which corresponds to the z direction of this electric field. So, now this is the extra term in my potential energy that the hydrogen atom will experience. Already this Hamiltonian, hydrogen atom's Hamiltonian, has got kinetic energy of the electron plus the potential energy of the electron with the nucleus. So, this potential energy is already there. On top of it, I have got another potential energy. So, I have solved this problem, that is the problem of the hydrogen atom, but I do not know what is the solution of this. So, this is my new Hamiltonian, the more complex Hamiltonian, whose solution I am interested in getting by using variational principle. Okay. So, now I defined my Hamiltonian. Let us look at what trial wave function can I take. Now, when you look at this hydrogen atom, you clearly see that the electron dense distribution is no longer spherically symmetric, rather it has got polarized along z direction. Now, to incorporate this into the system, what should I do? I would now have to mix my 1s orbital, which is spherically symmetric, with some other orbital. Which other orbital can I choose? If I consider 2s orbital, it will also be spherically symmetric. It will not allow me to describe this development of the dipole moment that I see here, this polarization that I see here. So therefore 2s is not a good choice. Since the polarization is happening along z direction, it is perhaps a good idea to mix my wave function psi 1s, that is a 1s state of hydrogen atom, with 2pz of hydrogen atom. So when I apply 2pz function, so I get some flexibility to polarize my spherically symmetric S function along z direction. So this C1 and C2 are the coefficients that will say how much of 1s, how much of 2pz should I mix to be able to describe this wave function. So therefore my trial wave function becomes a linear combination of two functions. What are these two functions? They are known functions. They are the hydrogen atoms 1s orbital, hydrogen atoms 2pz orbital. Now the moment I have described my trial wave function as a linear combination of two hydrogen atom orbitals, I know the task at hand becomes that solve these circular equations, or in other words, look at this 2 by 2 determinant and its solution. So in this, when I look at this determinant, I see that I have several integrals to calculate, the overlap integrals, the energy integrals. Once I have them, I can solve them and I obtain the energy value and the C1 and C2, and they will give me the idea about what is the polarizability of hydrogen atom. But the evaluation of these matrix elements as well as the determination of the energies and the wave function of this hydrogen atom, which is now subject to external electric field, is what we would consider in our next lecture. So in this lecture, we looked at a different variation of variational principle, that is the linear variational principle. Linear variational principle is used when your trial wave function is expressed as a linear combination of several known functions. The strategy of the solution of this linear vibrational method is simply writing down the n number of linearly dependent equations, or solve this n by n matrix. The eigenvalues and the eigenvectors would correspond to the energy and the wave function of that system. We would continue with our discussion in the next lecture. Thank you for your attention.